Thank you very much for the introduction, and thank you all for coming. It's nice to see that people are still interested about hearing about entropies. So yeah, I'll talk about entropy inequalities and the quantum entropy cone, specifically about this paper where we prove some new outstanding questions in the field. And just quick information, since the paper has been published, the title has changed to Tip of the Quantum Entropy Cone now. It's available on the PIL and archive websites, just to minimize the confusion. So I'll start by, since the results are pretty quickly stated, I'll start by motivating them a bit, quickly outlining the motivation for studying entropy inequalities and the quantum entropy cone, and this problem about whether one can downscale entropy vectors. Then I'll state the new results and use them to conclude various facts about the quantum entropy cone. For example, that it's not a closed set, a convex set. It's also not a cone, or a set of achievable entropy vectors is not a cone. I'll get into that later for a large enough number of subsystems. So just so we're all on the same page, I'll quickly review some notation. I guess it'll be kind of familiar since we've had a lot of talks about entropy so far, but rho will here denote a quantum state. And in this context, it'll always be on a finite dimensional Hilbert space, although I should mention that the new results are also still hold for infinite dimensional Hilbert space if the states and entropies are well defined. And then we define its von Neumann entropy as minus trace of rho log rho. And for multiparted states, we can define the reduced density matrices on subsystem X by taking partial traces over the complement subsystem. And I'll use this widely used notation of just specifying the subsystems of an entropy of a given reduced density matrix, since it'll always be clear from context when I'm talking about the entropy of a given reduced density matrix of some of the relevant subsystem. The only maybe new thing to some of you is these entropy vectors, which is defined as nothing more than just a list of all entropies of reduced density matrices for some multiparted states. So for a three-parted state over a system with subsystems A, B, and C, the entropy vector corresponding to some state rho will be nothing more than just a list of all the entropies of reduced density matrices. So I'll get like 3 single-party entropies and 3 bipartite entropies and 1 entropy of the full system. So I won't really spend time motivating this fundamental problem about finding new entropy inequalities because it's been done so well by previous talks, both in the information theory and plenary sections. I'll just briefly add that entropy inequalities have been called kind of the basic laws of quantum and classical information theories. So they're obviously of great importance, both practically and fundamentally. But despite intensive efforts, people have not really found any more. We're kind of stuck with these entropy inequalities, all derived from Strong's additivity. Strong's additivity was proven in the 70s, so more than 50 years ago. And these other basic entropy inequalities are sort of easily derived from Strong's additivity by purification, as we've also seen in previous talks. So there are basically no more inequalities than these guys. And maybe you've also seen them phrased this way. So there's a great interest in trying to find new ones. And to tackle this problem a bit more systematically, perhaps it can be useful to ask a more general question about can you find any new, just general relations between marginal entropies, so entropies of reduced subsystems for multiparted states. So this general relations can, of course, include entropy inequalities, but it could also be some more complicated algebraic relationship. And to study this question, it's common to define these 2 objects. So sigma n will here be the cone cut out in R2 to the n minus 1 of all vectors satisfying Strong's additivity and the related basic inequalities. So it's R2 to the n minus 1 because if I have n parties, there'll be like 2 to the m different subsystems, but I disregard the trivial empty set subsystem. And then we also define sigma n star as the set of all vectors in 2 to the n minus 1, which corresponds to the entropy vector of some quantum state for the multi-partied systems. So rho can here range over any quantum state for any finite dimensional Hilbert spaces. And yeah, it can maybe be a bit confusing. There's a terminology, sigma n and sigma n star, but it is kind of standard. But it's just important to keep in mind that sigma n star is the actual set of achievable entropy vectors that one wants to study. Then one can take the topological closure of sigma n star, which is proven by Pippinger to be a convex cone. So that makes it very nice to study in this context, the fact that it's a convex cone. But yeah, in the same paper as Pippinger introduced this proof, he also asked the open question about whether sigma n star itself is closed, whether we do need to take the closure. And this will later be answered in this talk negatively, that sigma n star is in fact not a closed set for n equal to 3 or greater. So this just shows that it's actually really important to specify that you're talking about the closure of sigma n star when you're talking about the quantum entropy cone, because the other thing is not even a cone. Okay, so I'll give a brief overview of sort of the current state of affairs in this study. So for two parties, it's not too hard to prove that sigma n star just equals sigma n, meaning that there are no more entropy relations than these basic entropy inequalities for two-party systems. For n equals to 3 or less, Pippinger in the same paper has then proven that the closure of sigma n star equals sigma n, meaning that there are basically no more entropy inequalities than these no more entropy inequalities than the basic entropy inequalities. There could potentially be more on the surface, on the boundary of sigma n star, which we'll actually also confirm in this talk that there are, but there are no sort of inequalities affecting a set of states with sort of non-zero measure in this vector space. The biggest open question perhaps is to answer what's going on for n equals to 4 or greater. So it is known that there are some entropy vectors that cannot be achieved by actual quantum states, which nonetheless satisfy the basic inequalities, as shown by Linden and Winter. But these are also states on the boundary of this set. So the real question is whether sigma n star, the closure of this set, equals to sigma n for n equals to 4 greater. And one might think that there are probably no more entropy inequalities than the basic ones. So I actually study this. So I'll just say that classically, this answer has actually been answered, or this question has been answered. And it turns out that there are more entropy inequalities, as we also saw in the one of the information theory talks yesterday, that classically these things all turn out, all these conjectures turn out to be true, and one can further show that this the closure of the relevant set of achievable entropy vectors classically is not even a polytope, so it's kind of like a weird smooth geometrical object. Okay, so before I'll state the new results, I'll explain what kind of motivated the study. And on this masterclass a bit more than a year ago, Andreas Winter conjectured that this very specific entropy vector could not be scaled down to 0. So he asked this question about whether it's always possible to downscale entropy vectors, which is basically asking whether the set of achievable entropy vectors is a cone or not. And it was conjectured that this entropy vector could not be scaled down to 0. So for this entropy vector, we have like all the single-partied entropies are equal to alpha, and the bipartite entropies are equal to 2 times alpha, the tripartite entropies equal to alpha again, and the total state is pure, so the total entropy equals 0. And notice that the mutual information, which is defined like this, for all single-partied states is 0 for this state. And this entropy vector for large enough alpha can in fact be achieved by this quantum state. It's not really important what it is, just that that for large enough alpha, this entropy vector is in this set of achievable entropy vectors, sigma n star. And this is an interesting question because it turns out that one can almost or always almost downscale entropy vectors. So to arbitrary precision, if we start with an entropy vector h vector h relative to some quantum state, one can always approximately scale it down to alpha times h rho. In this way, one can always exactly upscale entropy vectors by natural numbers, by taking tensor products, and then downscale it again by taking convex combinations. But with this downscaling, you don't actually hit the downscaled vector exactly, but you can still do it to high precision. And this was part of an important step in Pippenger's proof that the closure of the set of achievable vectors is a cone. So now I get to the new results. So we've proven that this weird-looking entropy inequality holds for all quantum states. So if it turns out that rho satisfies these weird conditions of total state being pure, the entropy of subsystem xi or x1 is not zero, and it has zero mutual information with all the other single-partied subsystems, then the sum of all single-partied subsystems must be greater than 1. So this is a non-homogeneous inequality because a constant is appearing here, and it's also constrained because these constraints run to the surface of the entropy cone because these are instances of the basic inequalities being saturated. And these conditions can be satisfied for n equals to 4 or greater, and one can also, by taking purifications, get a similar constrained inequality like this, where one has purified one of the systems and used this to prove it. And these constraints in this inequality can be satisfied for 3 parties or more. And here's like a kind of a picture about what's going on. So I'll emphasize that this is part of the surface of the entropy cone of 3 parties. It's not the actual entropy cone. That's like a 7-dimensional object. So this is like a projection on some of the surfaces of the quantum entropy cone. And the blue region is what is not ruled out by the basic inequalities and this new weird inequality. So you can see it has been sort of cut in the end. So this part would also be allowed if one just assumed the basic inequalities. And if you remember this vector conjectured to be non-scalable down to 0 by Winter, this in fact satisfy all the conditions from the new inequalities. So it turns out that it's as a consequence of this inequality, this does not belong to the set sigma 4 star for alpha less than or equal to 1/4. And similarly, the reduced state and 3 systems, which can be achieved for high enough alpha, as we saw before, does not belong to the set sigma 3 star for alpha less than or equal to 1/4. So this in fact proves that it's not always possible to downscale entropy vectors in the set of achievable entropy vectors. And yeah, one can also construct more complicated states that satisfy the conditions from the theorem in this way and have like a zero mutual information. It's not really, the important thing is just that these states exist. So there are instances of vectors that cannot be scaled down. So consequences of this, the first consequence is obviously that this sigma n star is not a cone for n equals to 3 or greater, because it's not invariant under positive scalings, which is just seen by the fact that there exist these vectors that cannot be scaled down to 0. And as a consequence, we can also conclude that sigma n star is not a closed set for n equals to 3 or greater. And this follows from the result I mentioned earlier by Pippenger, that the closure of this set is a cone, and therefore it cannot equal its closure. And it's also not convex, which also follows from this vector not being able to be scaled down to 0. And 0 is, of course, also always a member of this set, because just take a product state of pure states, then that'll be the 0 entropy vector. So these are kind of interesting results, I think. They're pretty negative, and basically they tell us that we can't really use these nice property of convexity and the cone property. But I still think it's kind of interesting that you can actually prove these things. And of course, as I said before, the question about whether sigma n star is a cone or closed or not was also left as an open question in this Pippenger paper. So since this is QRP, I should also mention some applications, although this is probably more like relation to practical stuff. I find it interesting that these the conditions from the inequalities are pretty similar to like a pretty general setup in a quantum secret sharing. So you can imagine a situation where Alice wants to distribute a secret to P persons, which we could call Bob 1, 2, 3, and so on. This could, for example, be the spectrum of a quantum state. And these quantum secret sharing schemes are set up such that individually the Bobs cannot learn anything about the secret from their state alone, but together, or sort of more people can actually learn the secret. And one way this could be set up could be to say that the quantum state of rho and one of the Bobs must be a product state. You could, for example, imagine that Alice sort of sends some random, or her state is known, but the state of the Bobs are sort of randomly generated by some known distribution. So measuring if one of the Bobs measures their state, they can in fact not learn anything about the secret. But together, if all the Bobs know their state, and if we assume that the total state is pure, they can in fact learn the spectrum of Alice's state by like Schmidt decomposition. So if we further assume that Alice's state is not pure, then we have exactly satisfied all the conditions from this inequality, which then tells us that the entropy of Alice's state and the entropies of all the Bob states must be greater than 1. Or said in another way, there is a lower bound on the information communicated. So perhaps this could help by sort of designing these setups. I won't go into too much details about how these new inequalities are proven, but it's actually not too complicated math. It's more like a brute force proof. So if you're interested, I would recommend that you took a look at the paper. It is sort of easy to follow, I would say. But the main point is just that we look at the largest eigenvalue of entropy states. And as the entropy gets smaller and smaller of quantum state, then the largest eigenvalue has to be greater and greater. So for states with small entropies, we actually, this way, know a lot about the spectrum. And this places some constraints on what the entropies can be. Yeah. Yes, and that's basically it. I also have some references if people want to take some pictures.
Thank you for the nice talk. We have time for some questions. I did have a question, so I'll ask it. Is there a sense that there are more similar inequalities out there, or is there something sort of special about this particular one that you've got?
We thought a lot about whether these could be generalized to sort of non-constrained entropy inequalities. But already the fact that they are non-homogeneous sort of is a bit troubling for this prospect, because, as I said earlier, the closure of the set of achievable entropy vectors is a cone. So if you had a non-homogeneous inequality that was not constrained, that would sort of entail that the closure could also not be closed. So that would in fact not be possible. And also, so we got some new inequalities for the quantum entropy cone when the number of parties is 3. And it's also proven that in this case, the closure of the set of achievable vectors is just what's cut out by the basic inequalities. So at least for 3 parties, this cannot be generalized to unconstrained inequalities. But maybe there could be some more inequalities out there. As I said, they're not terribly difficult to derive, so it's possible that one could derive similar constrained inequalities. Maybe. I hope so.
Thank you. If there are no further questions, let's thank Lasse again.